Welcome back. So, looking at this flap-wise forces and moments and age-wise forces and moment. So, continuing from the last session discussion that we started in the last session, we are trying to look at this now. For this, we, as I said, that age-wise forces and moments, this kind of mm, the age-wise moments gives rise to the power producing torque. So these are usually really less significant clockwise motion, but due to blade self weight, it can be quite significant in larger turbines. So for larger turbines, due to self weight, it can be quite significant. Okay. So let's say the mean torque, which is Q, uh, can be estimated as power divided by omega, which is rotational speed. Now, for an ideal rotor, what we can have Q is P by omega, which is 1 by omega, 16 by 27, half of rho pi r square u cube, which is 8 by 27, rho pi r square u cube by omega. So what we can do in the more general case, torque can then be expressed in terms of a torque coefficient, which is let's say CQ is Cp by lambda. Essentially is the power coefficient divided by the tip speed ratio. And so then what we can write, so using this, what we can write Q is CQ up rho pi r square u square. So what happens is that for an ideal rotor, omega varies with wind speed. So Q square of the wind speed. Now, if you have rotors designed for higher tip speed ratios, let's say the rotors designed for higher tip speed ratio operation have lower torque coefficients. Lower torque coefficients. Hence, they experience lower torques. So when we talk about lower torque, when we talk about lower torque, um, it is not necessarily uh, lower stresses, lower stresses. Okay. So again here, uh, according to this simple model, there is no variation in torque with azimuth. Okay. So that's how it. Now you can also this age-wise, or as we say, lead lag moment. So the bending moment in the edgewise direction, which is designated by xi at the rotor of single blade is m xi, can be a b. So there is no simple correlation for edgewise shear force. So edgewise shear force is xi. Uh, so the tangential force. So this is how this can be found out for this edgewise this thing. Now we'll look at the linearized. So now we'll look at linearized hinge spring blade rotor model. This is kind of an, I mean, kind of an which I mean one can just like an aeroelastic behavior of these rotor blades. So, which in a similar fashion, one could expect that people do in the helicopter rotor dynamics. So, um, here, since it's an rotated system, the wind turbines, this can get quite complicated during operation because your loads are variable, structure itself may move in ways that affect the loads. Uh, so now to analyze all such interacting effects, which one needs to have a very detailed mathematical model, or you can go for typical CFD calculations where you have detailed analysis technique or approach uh, to find out those things. But here, what we are trying to do is that we can use this simplified model for the rotor and examine its response to this simplified load so that this is more like an initial design procedure. One can use this kind of linearized system and estimate those forces, moments, stress, and all these things so that the first part design can be obtained. Uh, um, so the one that we will talk about here, which is primarily methods by uh, Stoddard. In 1987, they have talked about this. So this model provides good or in-depth insight not only into the turbine response to steady loads but also to cyclic loads. So this simplified model is known as the linearized hinge spring blade rotor model, or sometimes um, it's called hinge spring model. So both are same. So the essence of this model is to incorporate enough details to be useful, but it is sufficiently simplified that analytical solutions are possible. Okay, so it's a simplified model, but incorporating the interacting effects. Okay. Uh, so by examining the solutions, it is possible to have some of the most significant causes and effects of wind turbine motion. So this hinge spring model, it has four parts. Number one, that is a model of each blade as a rigid body attached to a rigid hub by means of hinge and springs. Two, a linearized steady state uniform flow aerodynamic model. Three, consideration of non-uniform flow as perturbations. And fourth component is sometimes an assumed sinusoidal form for the solutions. So this has these four components for this linearized model. So when we start with that, so the thing that we start with types of blade motion. So this hinge spring model allows for three directions of blade motion and incorporate hinges and springs for all of them. The three directions of motion which are allowed by these hinges are three direction of motion which are allowed by this one flapwise, two edgewise or lead lag, and three torsion. And the spring return the blade to its normal position on the hub. The spring returns the blade on its normal position on the hub. So that's what it is called hinge spring motion. So the what happens is that the hinges allow the three directions of motions, flapwise, edgewise, that is lead lag, and torsion, and the spring brings the blade to its normal position on hub. So that's what it's called the hinge and spring model or the simplified system. And as we have already talked about it, the flapwise refers to the motion. The flapping is motion parallel to the axis of rotation. This is the rotation. So Uh, Now the rotor which is aligned wind flapping would be in a direction of the wind or opposed to it. So it could be like this. So the one can find out the thrust forces along the direction, flapping directions, and then the stresses on the blades due to flapwise bending. Lead lag motion lies in the plane of rotation, so which kind of refers to the motion relative to the blade's rotational motion. In leading motion, the blade will be moving faster than the overall rotational speed, and in lagging motion, it will be moving slower. For lead lag, mm, in leading motion, in the leading motion, the blade will be moving faster than the overall rotational speed, and in lagging motion, it will be slower. This lead lag uh, motions and forces create fluctuations in torque in the main shaft, and with fluctuations from the generator. So mm, this is what is there for this. Now comes to the torsional motion. Torsional motion refers motion about the pitch axis. Uh, for a fixed pitch wind turbine, for a fixed pitch wind turbine, uh, torsional motion is generally not of great significance. But in a variable pitch torsional can was fluctuating loads in the pitch control mechanism. So what we would be primarily focusing on the flapping motion, and that lead lag and torsional motion, we can use the standard information available from the literature. So that's what we are going to use in analyzing this. So that means this simplified hinge spring model that we are talking about, that will have, kind of that known as this linearized hinge spring model. So it is simplified model, but essentially incorporating the interacting effects between the forces and the moments. And obviously, it has four basic components or parts. Essentially, assume a rigid blade and also connect to the rigid hub, linearized steady state uniform flow aerodynamic model, non-uniform flow as, if you have non-uniform flow, that considers as a perturbation, so that how that affects, and obviously some sinusoidal motion for solutions and things like that. And the blade motions, when you talk about in these hinge spring models, the hinge spring models allows three directions of the motions: flapwise, edgewise or lead lag, and the torsional. And the spring brings back the position on the hub. Obviously, flapwise motion happens like this. Lead lag motions are kind of going from the rotational axis. Obviously, there would be leading motion, there would be lagging motion. That is why we call it a lead lag motion. So in leading motion, the blades are moving faster. Lagging motion, these are slower. That is why you get this lead lag. And obviously, this will have impact on the torque and then associated shaft and the generator. Then torsional motions are there about the pitch axis. Then you can have fixed pitch wind turbine, variable pitch wind turbine. So if you have a fixed pitch, then the torsional motion is not that important. But if you have variable pitch, then this torsional motion can have some fluctuating torque loads in the pitch control mechanism. So these are all that, since the torsional and the lead lags are kind of obtained from the literature and all these, so primary focus would be on the analysis of the flapwise motions and all this. So that is what we are going to focus to derive this linearized system. Okay, we'll stop the discussion here and continue in the next session. Thank you.